Welcome. It's a big success, huh, this session. It's much more than I expected. So we promise we will not be too long because you all want to enjoy the evening, not miss the boat if you are on the gala dinner. So we'll be as fast as we can, but we have a few messages to deliver. So my name is Nicolas Freitag, and we'll have Hartmut Hangen and Puig Damians to and we present together what has been introduced in the latest in the new generation of Eurocode 7 regarding reinforced fields. And we start. Actually, we come from nothing because there was not really much useful in the previous generation of Eurocode 7 regarding this type of geotechnical structure. So it is a significant step forward for us to have this inclusion in the document in the clause 9 of part 3. The scope of this clause is it covers different things. It covers retaining walls, bridge abutments, load-carrying bridge abutments, reinforced slopes. So these structures, they have in common that typically they are made of several layers of reinforcement in between layers of backfill, compacted fill. But there are other applications that are covered in the clause, particularly basal reinforcement on soft soils, on potential voids, on rigid inclusions, and as a last application, the use of reinforcement along existing slopes, which is called veneer reinforcement. So as I said, there was no inclusion of such applications in the previous generation of Eurocode. Nevertheless, there is. It's not a new topic in the standards in Europe. First, we have an existing execution standard as a European standard, and we talked about execution this morning. And so this document, I think, was very helpful to have during this preparation of clause 9 because it provides a lot of vocabulary and of concepts. It dates from 2007. We have postponed its revision until this work on Eurocode 7 would be completed, and so I think it will be time in the next future to revise it, to put the documents in accordance to each other. In the different countries, we do have long-standing practices and existing standards or guidelines. Listing the standards, we have British Standards 806, Part 1 in the UK, not in line with Eurocode 7. We have in France a series of documents which are in line with Eurocode 7, current Eurocode 7. In Poland, there is a national standard. And we have national or regional guidelines, which do not have maybe the same level of authority, but which are spread in different countries. It's not exhaustive, and there are a few question marks sometimes, because sometimes these documents are emitted by some administrations, so are they the latest version? I'm not always sure. But I would say that there is a corpus of documents, and what is important, because we talk about what is included in today, what is included in Eurocode 7 Part 3, the new generation, but we will also mention what is not included, and there are quite a few things that are not included at European level that will need to be implemented in the national documents. So all these documents are deemed to be revised in the next future in order to have, in a specific country, let's say, a consistent list of standards. So reinforced field, I mean, for the rest of the talk today, I will not, the three of us, we will be talking only about the walls and slopes, so the first list of the first applications that I showed, and not about basal reinforcement or veneer reinforcement. For these structures, the clause 9 introduces some ultimate limit states that need to be checked. I group them in the way we are used to group them in France, but they are there is a long list of ULS in clause 9, and in the end, everything that is in my slide is somewhere in this list. And there are other things also in the list, but we are talking about external stability. This structure considered as a block, it may have an issue of static equilibrium, it may have an issue of global stability, that are failure lines that go around the reinforced soil mass. It can have an issue of sliding on the base, it can have an issue of bearing capacity of the foundation soil, and this is what we group under external stability typically. Internal stability is another family of ultimate limit states where we need to make sure that the reinforcement layers have no risk of failing by rupture in tension over time, over the design life of the structure, that they cannot fail by pull-outs, that there is no tensile issue at the connection, that the facing elements will not break. So all this included in what we call internal stability. And the last group of ULS that are considered are what we call typically compound stability, where we are considering through limit equilibrium method sliding surfaces that cross some levels of reinforcement or go along some levels of reinforcement. So they pass through the reinforced soil block. In terms of, and you will see more details because my colleagues will show you examples and implementation of these calculations, so you will have a better insight in a minute. Regarding serviceability limit states, of course, there are the same sentences for all the structures. We have to make sure that the behavior of the structure is displacement and deformation are compatible with the surrounding structures and their purpose. Could be, for example, the total settlement of this approach ramp compared to the rigid bridge on piles. We can have a step that is something that needs to be designed for. But it's also SLS comes also with the capacity of the selected system to follow the movement of the subground, for example, by differential settlements. You can see those lines. These lines, they were horizontal at the beginning of the construction, and after completing the works, there were settlements, and you see they are now curved because there is a longitudinal differential settlement along the ramp. And if you don't pay attention to that, you may have some issues with your facing system. So that's why we group this under SLS, plus many other things, like we will talk about bridge abutments and displacement at the bearings and things like that, which are also key elements. Regarding the justification, what is in the clause and its Annex F today, like I said, it's not complete. You don't have the full recipe to carry out the full design. There is a simple reason to that, is that there is one part of the equation which is on the resistance side, where there was, let's say, good consensus within the colleagues in Europe. On the other side, which is about calculation models, there are established practices in the different countries which are quite contrasted. So we deemed it preferable to just list these methodologies and then leave it to the national documents to be more accurate and finish the work. let's say we were not mature yet to specify one or two unique justification methods to be used all across Europe. So we did the easy job, and for the next 25 years, we have time to think about the next generation to do the harder work. But at the moment, what Clause 9 will provide the checkers for design verification is how to determine the formalism to determine the representative strengths, resistances, for tensile strengths, for pull-outs of different reinforcement materials. Actually, 3 reinforcement materials are covered by the document: geosynthetics, so geogrids, geotextiles, etc. Steel, galvanized or not, but we're talking about steel strips, wire mesh, ladders, which are typically used in this type of structure. And the last family is about the polymer-coated woven wire mesh, double twist mesh typically. And for each of these materials, a specific formalism is provided. Sometimes quite detailed. For geosynthetics and steel, it's quite detailed. For polymer-coated woven wire mesh, let's say there is the formula, but there's still quite a bit of work to be done to provide the actual values of this factor, because it is installation damage and corrosion of the wire below the plastic coating, and that depends on durability of the plastic coating and possibly damage of the plastic but not the steel during installation. So it's a bit complicated, and it doesn't go very far, but this has to be justified by the designers. For geosynthetics, just simply, we make reference to the technical specifications by ISO, which provide methodologies to determine the different reduction factors that are typically used for geosynthetics: creep, installation damage, weathering, chemical durability, and specific German factor, dynamic effects, which is used in Germany. On the other side, we have to determine the loads. We have the resistances, but we need to determine the loads. This is where it's more vague, but we have in the clause we have a table of factors that provide sets of factors for MFA and RFA. And this is quite important because we do have a specific additional stabilizing effect in our structures: pull-out, tensile strengths, facing capacity, etc., connections. So all these are listed, and the factors typically depend on the type of material, or sometimes they are, let's say, hard-coded in this table, which is an NDP. So the national documents will also have to confirm or amend these values. So I said what I wanted to say for this introduction. We'll have Hartmut first to show us examples on walls and slopes and some consideration, and then Ivan will will present his work of benchmarking on real cases after that, and we will have common conclusions at the end and questions. Thank you. So Hartmut, it's your turn.
Yeah, Nicolas, thank you very much. As Nicolas already has said, Ivan will take care for the real structures, the vertical walls. I have the easy part. I think it's complex enough, for me at least. I will do a steep slope, or a slope, and the that already brings us to the first question. What is a wall? What is a slope? I cannot answer. I've looked up in what we have already on the market in the standard cases, because EC7 does not tell us. So I would say EC7 for me, in my interpretation, is a big bracket on both sides, which gives us a lot of freedom, but at the same time, freedom means a lot of responsibility, and I think this is what we want to bring also, especially with the example of Ivan. He will be talking about how to do the design using modern numerical methods, and I think it is a lot what we can do. It's a huge opportunity in future because we have the bracket, and that will help us in getting acceptance in many places. So a slope in the UK is a structure which is about 20 degrees from vertical or flatter. The same, maybe the Dutch have copied that. I think so. It's the same definition of what is a slope. So we do a slope. So this is now defined because the structure which was selected for the example is looking like this. So it is a 70 degrees a wraparound structure. You can see that the geogrid is always put in different layers. So typically it's 50 centimeters, and you wrap the structure at the facing. There is one missing. Okay. Right. So we will see how this can be done in reality in some pictures later. So, if we want a calculation for that, we need to understand how do we start. Of course, all the things which have been discussed all this morning, we need a proper ground model, we need proper loading, and for that we have common understanding that we will be looking in the other clauses for sure. As Nicolas already has said, there is a list of relevant ultimate limit states and serviceability situations which we have to check. But I think not everything corresponds to every problem. So this is the difficulty, and we have to understand where do I need to do something. I can imagine a proof checker, a bridge designer in Germany. He will be looking, this is everything I have to check, and you have to check everything. So this is my fear, because it is listed there, and he's not thinking of what is really required. So, and it will continue with the question, do I go for MFA or RFA? And the difficulty will also be which is the right design model. So I said it's easier with the slope, but I will also only look in the rupture of the reinforcement, so internal stability, because I don't want to show what we have seen before. Bearing failure should be the same, but I will outline a little bit on the influences of the reinforcement to the bearing failure check. So this is what I wanted to show you before. So we are going to talk about reinforced soil structure where the geogrid is wrapped back, and we have a formwork, a temporary formwork in the front, which helps us to do the compaction. So in reality, it could look like this. This is a very heavy one with a steel formwork, so very comfortable. I only saw on a railway structure in my life. Oops, so there it is. But typically you can use a wooden formwork or comparable things. So you have the geogrid and the non-woven preventing the soil to fall off if you do not cover like was foreseen here. So I have chosen this example because I don't want to think about the facing. In this case, what typically you have seen already, you should think. And then we have seen these nice pictures before. So we have to check the material of the facing. So is it concrete? Is it reinforced concrete? Is it unreinforced concrete? We have a lot of freedom, but again, a lot of responsibility. Everything needs to be checked. And that does mean we have to think in concrete, we have to think in steel, and maybe in wood or whatever material, because the code even leaves a lot of freedom to use other materials in future. So if we had a facing connection, then I think we have again a good bracket, because we can see that we have the possibility to estimate or calculate or check the facing either by calculation or we can do it in a test. If we did it in a test, we can see here a combination of a Gabian basket mesh and the geogrid, and it is connected via a bar. And if I go back one slide, you can see we have a reinforcing element, which can be the reason of the failure. We have a connecting element. This could be a steel bar, it could be a plastic bar, whatever. And we have the facing element itself where the failure can happen. So this is what we can see here. Here it's the geogrid, which is the weak point. And here we can see that the steel bar is the point and everything is related. So that's the nice thing about it. But the good thing is we do have partial factors for that. So now we have at least a base where we can look for, and the materials are mentioned, and it's mentioned that this is a thing which you have to check for. So if I go back to the example, yeah, there is a lot of freedom of how we should calculate the strength and reinforcement. So it can look like this, and we will, or I will go in my example for the slope stability method. So the rest of the methods is left for Ivan. So I have the easy one, and as Nicolas already has shown, we have failure around the structure and failure which is passing through the reinforcement. And since slope failure is considered in MFA, I thought, okay, I go the easy way. So I will also design my geogrids in MFA. Okay, that's easy. So I look in the partial factors table and I can see material factors approach. This is there. Okay, ground properties are reduced, tangent phi, and so on. This is nothing new. But maybe you can see the pull-out resistance of one of the resistances, which of course I have to check. This is not factored, so let's see what that means and why it is like this. Then there was a lot of discussion about the magnitude of the material factor for the strength, tensile strength. You can see 1.25. That was a lot of discussion, and it will be a lot of discussion. I'm pretty sure Germany will go up again, and maybe Italy will go down, I don't know. But let's see. Yeah, so as I've said, there are a lot of things which we can look in, and I said we want to go for slip circle analysis. But if we look into clause 4, there is so much freedom again, so I can go for this and that, and again I have a lot of freedom. So I went for Bishop in this case, and I would say there's a lot of work to be done on the national level to see what we should do when. If you're confused, like I was confused about so much flexibility, then maybe you can get a little bit of guidance in the Netherlands. So we can see of different structures. So our steep slope, it's a flower Hellingen, and rec bar reinforcement means it is a geogrid, it's a polymeric material and not a steel material. So it does have a lower tensile stiffness than a steel reinforcement. And in that case, it says, okay, you can go for global stability analysis, or you should do this, and use the sliding circle. Right. So the problem starts with the definition of materials, of course. We have soil, we have reinforcement, and we have soil plus reinforcement. This is the interaction. Does the EC7 give us guidance on which soil I have to take, which parameters I have to take, which angle of friction? Is it peak or residual? Is it possible to use cohesion, yes or no, or maybe 50%, or what is it? Can I increase the shear strength close to the facing, like you can have the chance in German slope stability standard DIN 4084? That's possible. And it helps a lot to exclude surface failure. What is the degree of compaction I should use? So there are a lot of questions, and part of the questions are handled in the application standard 14475 or the Earthworks standard, which of course we should not forget. So EC7 is not a cookbook. For those who are familiar with cooking, Paul Bocuse, I borrowed this. So those who missed the boat, there is an alternative, I guess. Right. So if we look in the application standard, there is a little guidance of what soil you could use. Yeah. So you will see the same slide, but different markings in Ivan's part. So we have type 4. You can go for relatively marginal soils because you have a flexible facing, we have a flexible deformable reinforcement, and the slope is not very steep. So for sure the fill should be compactable. Yeah? So just as a small reminder, yeah. So if so, and especially if you would have a gravel like this person there had, we will have to see for the installation damage and how to establish the design strength of the reinforcement. And this is something which is new, I would say, at least for the Germans it's new. It's the ISO TS. So it's a technical standard how exactly you should implement and derive your reduction factors. Nicolas has shown the list of reduction factors, and unfortunately we need to go a little bit more into the detail to see what is new in that reason. It is interesting because we can consider now, going more into detail, the knowledge and the quality of data. Let me try to explain this. So we have a factor of safety. Unfortunately, in the ISO TS, it's called FS. It's safety factor, but it's the gamma, as you can see here. And it is depending on the time. If you look for R, the small r, it's the time to design and the time maximum which you observe your results. So it offers you to bring into your design how long you test. So like for me, I'm working for a company, I'm 25 years in the business. I know that we have started testing even before I started, and still tests are going on. So I can take the time to rupture for a creep rupture, which is the major effect. I can put 25 years, and you can see if you do this calculation that this factor R1, so which is then to be added to your safety, is reducing the more you know. So before in Germany we had 1.4 and you cover everything. So this is unfair for those who do testing and good for those who don't do testing, but I think this is a major step ahead in evaluating. Nicolas also has mentioned that there are some new things which we have brought, and this is a reduction factor for dynamic impact. So this is only valid for railway structures. We are fighting to bring our reinforced soil structures into SNCF and Deutsche Bahn. And I think this can be helpful to convince these people that we analyze the impact of dynamic loads for the reduction of the strength and the stiffness. So this is the reduction of the strength, and now we have a factor which is allowing us, if we test it, to reduce it. And the good news is that for polyester materials, for example, this factor is nearly 1. So it is good, but we, if we go for other polymers like polypropylene, for example, it is not like 1. So you need to look in detail what reinforcement you are using. Okay, so we have the soil, we have the reinforcement, and now we are putting both together. So we are talking about interaction, and interaction is either pull out or direct sliding. You can see from the graphs which we have considered here, this is pull out and this is sliding. I will only talk about pull out here. So what we need to know is the factor describing how good the interaction is. And this is this interaction factor. So we have the shear strength, we have the vertical pressure, and we have a factor describing this interaction. This is not new, but we have to test it, either like this, or like this, more sophisticated. But you may question, how about the safety in the data? I've told you about long-term testing about creep rupture. Would you put a factor of safety on pull-out? Huh? If you go for the material factors approach, we don't factorize this interaction. So this was new for me. We always had this factor in Germany, but obviously there was a lot of discussion to avoid double factoring. Because if we go for the material factors approach, we have safety on the shear strength already. So if we implement another gamma here, gamma pull out, we would have double factoring. We've tried to understand what's the impact in our example. So I've made a calculation there. On the left side, this is the normal way, Germany 1.4, and this is the new way, EC7. And you can see the degree of utilization is exactly the same in this example. So if we look more in detail, so you can see that the software has factorized the design shear strength. So this is the more optimistic, and this is the German strength. So you can see that the software has implemented this, but maybe it's a different situation if you look for veneer stability, which we do not cover here in this comparison and this analysis. So it is good that we have the other opportunity, and then it's the duty in the national work that those problems then should be excluded to be considered in MFA, but RFA. So this is what we have to take care in the local situations. Now, what is not considered also, but it's important, is, for example, that we look for the details of the calculation. So we have checked about different number of slices. So it looks like if you don't have time, only 5 or 7 slices, yeah, there is not a big difference in this case. But if you compare it for a different structure, it might be another case. So yeah, so be careful with all these details, which are again not included in the Eurocode 7, but this is common sense. Looking for the adequate mechanism. We have this freedom. You have seen the list of potential models and mechanisms I could use. So if I didn't knew that there is block sliding method, I would go for slip circle analysis. But assuming I would have a weak layer here, so could be a geological layer or could be an artificial layer like a geomembrane or whatever, with a very low shear strength. So you can see that this is a tremendous difference. So again, it's not a cooking book, it's just the brackets. Same if I go for bearing failure of the ground. So this is a calculation we have performed not as per the new guidelines, but the old. But I would assume that the outcome is the same. So because we have to check for bearing failure in this structure, right? So a classical, nothing with slip circle analysis. We check the bearing failure as it was a massive structure. So we will see it's 1.08, so we are not happy. What do we do? Typically, we prolong the geogrid, the lower layer. Okay, we are at 87%. Everything is fine. I can go and have some beer. So only making the lower layer from 9 to 10 meters. So, but is it truth? I would say it's difficult to say. You have to check global stability using other methods as well. And you can see that the slip circle analysis is not happy with 9 meters. So I prolong to 10 meters and we're still not happy. So what do I have to do? I have to prolong more than one layer. So this is the challenge, and I'm pretty sure that here the factorization of pull-out will have an impact. By the way, these reinforced soil structures are performing very well, as you can see in this analysis performed at Technical University at Aachen. So we have compared the bearing failure of a reinforced soil slope and the stiff structure here at the bottom. And we can see on the left graph, this is the vertical stress and the vertical deformation and the horizontal deformation in the right part. If we just look for the left picture, we can see that the load deformation behavior is quite similar of the stiff and the soft structure, but we can accommodate a much higher vertical stress in the soft structure, which we explain, and you can see it here from these PIV pictures, that we can mobilize much deeper shear planes than we would observe in a very stiff structure like a cantilever wall. So it is moving, and I think this is a huge effect, and it should reflect in our design guidelines also. Maybe one day we will not have this typical bearing failure check in that way we are using it. And if you do it properly, it should look like this. And I can conclude my part with an intermediate summary, so that we have a lot of opportunities, and that we do have a bracket for the definition of material resistances. And in the GeoGrid part, it's much more specific than it was used to be, as it allows for the impact of, to consider the impact of dynamic actions. And we do have a way to handle connections, which is a very important point. And yeah, we have some specific things like ponderation of pull-out, but at least for the slope compared to what we used to have, it's not a revolution, but it is something, I think, which will help us to improve for the future. Ivan.
Yes. Okay. So, real case study, as Nicolas introduced it, for reinforced soil walls. I will briefly introduce the outline. I will just present brief issues, from, not issues, but just a few characteristics of this project, just to locate ourselves in the case study. Then I will go through internal stability, and I will compare analytical approaches. I will include sort of numerical approach in terms of ULS, and then finally I will conclude with some sort of serviceability linked states on this same project. So the project, I just focus on this huge project in Bratislava, which includes lots of reinforced soil structures from many types. I mean, many times the configuration can be back-to-back, bridge abutment, regular reinforced soil structure, a slope on top, simple walls. So I selected two that they are one with steel reinforcement, another one with polymeric reinforcement. Okay, these are the ones I selected are not bridge abutments. Okay, I don't want to confuse anyone. So they are just regular structures in where you have slope on top and similar wall height. So among all the ultimate limit states required, I just focus on tensile strength and pull out. I will also only focus on coherent gravity method and TRAG, but I will include later on the numerical analysis. I forgot to include this later on, so keep in mind these other methods. Other methods because in the analytical comparison I will include other methods. Other methods. So for the coherent gravity method, we have to check the annex in where there is this figure that summarizes more or less the philosophy of the method, with the two references that we have in the European framework, in where you can find a very good explanation of this method. Slightly different depending on some factor, depending on the reinforcement type, but more or less the same. Coherent gravity method, there is a sort of, I wouldn't say arbitrary, but there is a sort of convenience that we consider it's suitable for unextensible reinforcement, non-extensible reinforcement, and this non-extensible reinforcement is defined by this 1% strain. Could be 0.5, could be 2%. I don't know from where is this 1%, but in any case, this strain 1% is almost not relevant because the extensibility or not extensibility of a reinforcement plays a role in comparison of the strains that can develop the soil itself. If the reinforcement moves along with the soil, it's extensible. If not, it's not extensible. So this 1% maybe it's a bit restrictive because we know that typically a well-constructed reinforced soil structure with regular granular material, typically when it fails, achieves a strain about 3–5%. So 1% could be a good limit in the lower bound. In any case, this means inextensible reinforcement, which is typically related to steel. On the other hand, we have the T-back wedge method, which is more related, or actually related to extensible reinforcement, as we said. I am missing a reference, a code reference, as it happened before in the coherent gravity method, which has a reference to the French code and the British standard. The T-back wedge method has no reference here to check what happens. But we have it. It's quite good explained in the British standard. You can see that the picture is quite similar with necessarily this definition of 45 plus phi halves for the ranking, active ranking. In any case, it's not given. I don't know why, but could be. Again, in extensible definition, we consider extensible reinforcement when the strain is more than 1%, which includes typically geosynthetics. We can discuss if this type of reinforcement sometimes could be treated as a non-extensible, because they are quite stiff, and as we said, typically when you include all the factors in this kind of reinforcement, you are playing with them in a very short range of strains, and far away from the, not far away, but less than the strains that can develop through the soil. So maybe at some point we can deal with them as a non-extensible. In any case, here is extensible. So, okay, this is material properties of this project. There was a sort of convenium for the friction angle coming from triaxial. All the values were higher, but the client won a deal of using 35. I think that the lowest one was 38, but it's just a convenience. These things happen as in the client dealing process. Sometimes you agree in some values that are previously factored before starting the analytic. Okay. The same with the gamma. Gamma was established as 21, I think, just well, it doesn't matter. So our soil could be categorized as this type of soil, granular, good soil, no fines, no plasticity, and in our applications we are in the range that all are often used, so you don't need to move forward with external testing or so on. So analytical approaches, basically the original one was for the steel was the coherent gravity method according to the British standard. So we can compare with the coherent gravity method, British standard, but with European Eurocode 7 factors. Coherent gravity method, French standard, same for including Eurocode 7 factors, and these two methods that belongs to the ASTO, the American code, including European factors that maybe for the simplified can have a chance to be used, but for sure not the stiffness. The stiffness is surely you are not aware about what this method means, but this method comes from a purely empirical procedure of development. I don't know if it will be applied a lot in the future or not, because it's quite shaking minds in terms of a new methodology to design. But in any case, I am concerned that it's wrong to use these factors with a method that includes its own factors. Okay, so these are the three codes I am using. the main equations to generate the tensile strength for the stiffness, simplified and coherent gravity method. And we have here the original solution. The original solution, factoric coverage demand ratio, which is a term that I put here, but it's not established anywhere. It's just because the coverage demand ratio is including already factoried values inside. So obviously should be higher than 1. Should be higher than 1, and as close as you are to 1 means that you are optimizing your solution. Okay? So we can include here all the remaining 4 methods included. So we are more or less in the same game. Okay? No, I think, of course, the stiffness, as we said, the stiffness is the one that goes maybe behaves a little bit weird, but we are almost in the same game. If we do this with the polymeric, what I did is fix it first the number of connections, which means the number of strips per panel width, which was 2.5, and play with the grade, playing with the established base characteristic strength of the strips. And then I fixed the grade and played with the number of strips. Right? It's just two ways to understand or to analyze this sensitivity. So I include the TF wedge method because it's extensible. Okay? So this is the original solution, was from the first layer to the bottom layer, different grades, 30, 30, 27, 36, whatever, and different number of connections. So we can compare with the different methods used. Right? We can see that almost the same, 3 connections, 4 connections, almost the same, but the stiffness method, the stiffness method, I think it's a bit critical in comparison with the previous ones, because it gives you only 2 connections at the bottom, okay, 1 connection on top, so you cannot install 1 connection because the panel will move freely laterally, but in any case, it's the solution that you can get in terms of a number of connections if you fix the grade. Okay? If in the opposite way you fix the number of connections but play with the strength of the strips, you can get this. Almost the same, comparing with the coherent gravity method for the French code. Almost the same also with the simplified method, but similar, but critical, different for the stiffness. Stiffness is saying that you can use 36 when the French code is using 70, for example. So it's a huge difference. It's almost double, almost half for the stiffness. So numerical approach, we jump to the numerical approach. General, we have, we can use it. It's the first time that maybe a code officially established this numerical method as a verification for ultimate limit states, as long as they are validated. Validated, we have here the different criteria of validation according to the level of validation, but I think we are all familiar with this calibrate concept, site observations, relevant design situations, blah, blah, blah. Okay? So, numerical models, maybe the nicest sentence you can read here is this, that sometimes you don't need complex models to achieve a good solution, a good calibrated solution. This is quite clear, but sometimes it's, at least for the people that it's not related to numerical model, they want to complex constitutive models. Sometimes you don't need it, so depending of the case study you are analyzing. So, for the verification of ultimate limit states, we can extend the explanation, but this is not strictly related to reinforced soil, this is related to other structures, so we will use the recommended one, which, just take this into consideration because I will use it later on, okay? But the recommended one, you have first step to analyze your problem with the representative values, and then second step, analyzing your problem with the partial factors M2. With, if you go to the node D, with a reduction strength process, or establishing initial equilibrium, including partial factor M2. So, what values of M2? You can go here, and you can see here that intended to be used for numerical models, so it's 1.25. If you include the consequence factor, you can go up to 1.4 or 1.1, okay? Lower, higher, description of consequences, whatever. So, you do this, reduction strength or equilibrium with M2, and you can continue doing this at every stage you consider that it may be critical for the ultimate limit states. Okay, so you don't have to do it. This is particularly interesting in numerical models, because in our numerical models and our structures, because our structures are clearly stage construction structures, okay? Very related to the construction sequence you to perform. So you have to use this for each, no, maybe not, just select the critical ones, or I don't know, the criteria, but of course not all the stages has to be verified in this way. So now you are expecting the same example in the numerical model way. Sadly, I had no time to do it, but I have done this with a very similar structure, okay? The similar structure is this structure, is 10 meters, 0.5 as a height. And we used a calibrated model using CodeBright, which is a finite element model that we have in UPC, in the Polytechnical University de Catalunya. The model includes all the main things that we know are relevant for this, for the behavior of these structures, which are the bearing paths between panels, interfaces, connection, whatever. Okay? So we are going to compare, again, stiffness method, simplified, and coherent gravity method. We can design our structure according to analytically and code-related equations, and we can get for the the solution A, which is the stiffness method, all our layers. Now the number is reversed. The first one is the bottom one. I realized this. In the previous schema, the first one was, well, doesn't matter. We have 25 in all reinforcements. In the second option, simplified method, we have 25 in some of them, 30 and 40. And in the coherent gravity method solution, we have 25 top 1, 30 and 40. Okay? So if we plot this, we have this plot. We can see clearly, and maybe this explains why the stiffness method is going that low in the previous table. We can see here the simplified, the coherent are not the same but similar, but the stiffness is going clearly down. Okay? So it's different, considerably different between both philosophies or the three results. If we include the numerical method results, we are even lower, okay? So, and increasing, because there is a sort of tricky issue on determining the stiffness of the polymeric strips, because the polymeric strips, there is not linear, and depends if you take secant modulus or tangent modulus, and the value of the strain you want to consider. It can change a little bit the stiffness, and this is irrelevant for the numerical methods, at least for serviceability. For this ultimate limit stage, there is not a lot of changing. There is not a lot of change if you use one stiffness or 1.5 the previous one. So we can look for this. We have these results, characteristic value, representative values. Okay. So we can include a material factor, and even assuming 2 double, there is not a big change. There is a change, from here to here there is a change, but we are still far from the trend of the stiffness method. Close, but still the stiffness method is conservative, being the one that in the previous solution gives us a very lower amount of reinforcement. Okay, this is the position of the maximum tensile load. It's true that maybe this is the maximum, okay? But probably we have sometimes you have a maximum at the connection and then another maximum or close to the maximum in the line. This is quite representative to the so these values probably, if you check the second one, it's about here. You can see that. Okay, so last part is a numerical approach for serviceability limit states. You have this full also descriptions for the serviceability limit states. There is no clear explanation about how to do it, but if you check the previous table, you can see that note A is saying you that this is maybe the combination you should use, representative values, to check serviceability limit states. So, in this case, of course, it can be omitted if it's not required or not representative. Right? This is again the same project, a bridge abutment, a real bridge abutment, and we have defined the model according to the reality. So we have also the material, Some ones coming from test, but as we said, the 35 it was a sort of an agreement between the client and the designer, assuming polymeric strips grades 65 and 70. This will be relevant because I will change it later on. So, construction stages, we need it, excavation, first layer, second layer, third layer, reinforcement, blah, blah, blah. We can go on, we can install the bank seat, then retain it fill on top, going up, pavement, bridge deck installation as a load, of course, then bridge deck plus traffic loads, both on pavement and on the hypothetical bridge deck, and horizontal load, because the deck needs this horizontal load application. Okay, we can do this, and we can go as detailed as we want, but it's not the point here. So we can have different results, nice results. Numerical modeling likes to see, because you can have these shear shading results. You can see, as I said, this 3% that could be a reference. This is the value that I used to use as a reference to check how far I am from failure. Regardless the reduction of strength, if I have a 3% clear shear shading crossing my reinforced soil block, the equilibrium is weak. If I have equilibrium, means 1.0 nothing. So this is quite a good value to get a reference on how to analyze the results obtained in this beauty colored shape. Okay, so this is the facing. One comment here. Typically, facing deformation, facing displacements is a thing that the client likes a lot. Give me the facing deformations, but we have seen that these type of structures are very related to the construction sequence. So you cannot control this you cannot trust these results in a very, very strong way, because the construction sequence, sometimes you rectify the displacements that you get in the previous ones. And in the model, you cannot do this. The model is just straight, going up. Okay? So these are the results we get for these strip grades 63 and 73. Results also displacement in terms of the point in where we apply the bridge deck. Okay? We can see that the maximum facing displacements here for this model was about 10 centimeters, which is quite a lot, Okay? Also, there was a reference that we could not exceed 5 centimeters. So, depending, we will discuss this, but if this is established, we are far, we are double, almost double. But the criteria was serviceability limit stage. And this 10 centimeters is including 100% of the traffic loads. So we can discuss if this is right or not. In any case, we have the model, we can increase the grade of the reinforcements, 100 kilonewtons, we reduce significantly the displacements. What is true is that if we assume steel, the displacements are almost negligible. Okay? So, again, this is assuming 100% of the traffic loads applied in both pavement and on the bridge deck. If we check Eurocode, this is not right. If you check the serviceability limit stage, you don't have to apply this 100%. Actually, you can apply 0% of the traffic loads. If you check the British standard, typically for the serviceability, you only apply dead loads. So traffic loads are not to be applied as a serviceability limit scenario. Okay? So if we consider this serviceability limit stage without these 100% traffic loads, the results are these ones. Okay? So we are in the original case, we are about these 5 centimeters maximum, established maximum, arbitrary but established maximum displacement that the structure can respond. So it's true that British standard does not include this facing deformation as a serviceability limit state consideration. So we should follow the British standard at that point. And what is actually said in British standard is that the post-construction strains should be not larger than 0.5. This post-construction, there is a sort of discussion, what does it mean? What does it mean, post-construction? So in our case, because we have a bridge abandonment, so this is for the wall, this is for the reinforced soil block. So it can be estimated from once you finish the wall, then you install the bank seat and so on. This can be the post-construction strains. Okay? This is the reference to the British standard, and this is also a figure from the British standard. So let's check what's the strain. And if we take into consideration the two more loaded reinforcement layers, we can see that our strain is lesser than this 0.5. So we are in this range of values, regardless the facing displacement. Okay? And even more, if we check the maximum point in our reinforced soil structure, we have this 55.6, and according to the grade of the reinforcement, we are about 2 times or even 0.25% of the characteristic strength, which is a lot. This is assuming the 100% traffic loads, which, as we agreed, is not a purely serviceability limit states according to the Eurocode. If we assume no traffic loads, we are about 6 times safer. So this, in addition to this, I think that our solution is okay. Our solution is okay. Another comment now. As we said, the friction angle was assumed as a convenium 35. But if we check the previous version of the Eurocode 7.1, we can see this beautiful sentence. The behavior of materials assumed in displacement calculations should be calibrated by comparable experience with the same calculation model. This is not anymore in our current version. Another sentence that I like a lot from the Eurocode 7 Part 2 is this one. The triaxial compression and direct shear tests provide commonly accepted strength parameters which may be applied to routine design methods, but which are not necessarily applicable to other analyses. This is not appearing anymore in the current version of the Eurocode 7.2. And we like it. We like it because if we check, for example, British standard, this is a full development about what Hartmut said, about what angle we should use. Plane strain, and peak value. You cannot design on this because this is your working scenario will be always in before this peak. So I am missing at some point in the Eurocode 7 Part 1 and Part 2 some sort of open or at least plane strain citation that is inexistent in the current version. There is no plane strain citation in our current version. So if we believe this, traditionally I think it's quite well established, plane strain conditions, we can check that we can relate this plane strain with triaxial with, this is quite old, but with testing or some bibliography literature references, okay? We are about from 1.1 to 1.15 times the triaxial for the plane strain. So let's see what happens if in our model we assume this plane strain coming from this 35, which is clearly factored already, arbitrary factored. Let's check what happens in our model if we assume this 40 degrees as a friction angle. This is the previous ones, friction angle of 35. This is the current ones. The current final solution, according to plane strain, maybe, I am pretty sure it's more representative to the reality, we can reduce a lot these facing displacements under real serviceability limit states scenario. As a reference, I can include the steel that it's not in the order of magnitude, still with triaxial, but we are close to the steel triaxial results. Okay, so Nicolas, your turn.
You can breathe.
Yeah.
Thank you. You were super fast. We have some time.
Yeah.
I can take my time for the conclusions. No, but you've seen in a very condensed way a lot of questions arising from what you have in the documents and why we need these national documents to complement the clause 9 of the new Eurocode 7. It's not a surprise, we knew it, and that's why we need to revise the list of documents that I showed at the beginning. And if we list what we need to, there are plenty of things that have been said, of things that we need to provide. So calculation models, related factor approach, NDPs, because you were saying about double factoring, but actually not factored is an NDP. So Germany may decide to put 1.1. I hope not, but it's a possibility. It's a possibility. Specific calculation method for specific structures. I mean, bridge abutment you were mentioning, horizontal loading on top with traffic barrier, seismic is a little bit under question now because what we will find in Eurocode 8 will be very, very short. So we need to probably provide some calculation models, not safety levels, but models in our documents. When or not to use numerical models. Let's not pretend they can be the solution for everything, because I could spend hours with Ivan discussing his models. I don't trust your models. But, but no, but it's typical reaction. I mean, your difference is so big compared to the conventional method. Of course, we would need a lot of questions. How do you do that and that? And it's endless, because we are talking about day-to-day, more or less routine work for many of the structures we've seen, and we cannot enter in that kind of discussions with the checkers, between the designers and checkers for common structures. They need to be focused on the cases that are not covered by classical analytical model, complex situations, and there are plenty also. And also some default values for some parameters. We like to have in our standards some penalizing default values for the promoters of systems who have not done their homework about testing their materials, and that is not something we can do in Europe. We could do in Eurocode 7. We have to do it related to the calculation methods. You talked about plane strain. It's not plane like that. It's another plane. Plane strain against the triaxial, opening to alternative materials. The sustainability is a very important topic. With our reinforced field solutions, we have very interesting solutions in terms of overall impact, and we can be even better because the field can be made of recycled material or site-wound material with some treatments, etc. So that is also something that needs to be considered, particularly probably in the revision of the execution standard. But it's also related to the design, definitely. And as a last personal note, and finally it's an echo to what I was just saying regarding the numerical models. We have to be careful about a run in optimizing excessively compared to the existing practice, the structure, specifically with extensive reinforcement. The more load in the reinforcement, the more displaced deformation. And then we would then be led to do more and more SLS, more and more numerical analysis, and waste more and more time just for a little saving. So just want to be a bit careful about that. These are my words. I think these conclusions are shared by my colleagues, but if you want to add something, don't hesitate. Otherwise, if you have any question, comments, we have a little bit of time before we